Picture two part-time jobs. In job A, every single day you earn either 900 rupees or 1100 rupees, each with probability 1/2. In job B, you earn either nothing at all or a full 2000, again with probability 1/2. Now here's the twist. Both jobs pay the same on average, 1000 rupees a day, and yet nobody would call them the same. Job A is calm and steady. Job B is a gamble. So one number, the average, clearly isn't enough. To capture both the center and the risk, we need three ideas working together: expectation, variance, and standard deviation. Let's build them. First, the object we're measuring. A random variable is simply a number whose value is decided by chance. We write it with a capital letter, x. Today, x is discrete. It lands on one of a list of separate values. Each value x carries a probability, p of x, the chance that x equals that value. This list of values and their probabilities is called the probability mass function. Two rules always hold. Every probability is 0 or more. You can't have a negative chance. And across all the values, the probabilities add up to exactly 1, because something is certain to happen. Expectation is the long-run average, the value you'd settle toward if you repeated the experiment forever. Its formula is beautifully simple. Take every value, multiply by its probability, and add them all up. It's a probability-weighted average. Likely values pull the average toward themselves. Rare values barely nudge it. And if every value were equally likely, this collapses to the ordinary mean you already know. Let's see it. Here is a little probability mass function, a bar chart. The value 1 has probability 1/2, so its bar is tall. 2 and 5 each have probability 1/4. The height of every bar is its probability. Now the magic. Imagine this chart resting on a knife edge and slide the pivot until the whole thing balances. The point where it balances, that is the expectation. Watch it settle. Run the numbers and it agrees exactly. 1 times a half plus 2 times a quarter plus 5 times a quarter gives 9/4, 2.25. That's precisely where the pivot came to rest. Expectation has a property that makes life wonderfully easy. It's linear. If you scale x by a constant a and shift it by b, the expectation scales and shifts in exactly the same way. The constant a slides straight out in front, and the added b just rides along untouched. So to find the average of 2x minus 1, you take the average of x, double it, and subtract 1. No need to touch the probabilities at all. And here's a bonus that surprises everyone the first time. This holds no matter how the variables are tangled together. The expectation of a sum is always the sum of the expectations, dependence or not. Expectation gives us the center. Variance measures the spread around it. Called the mean mu. The variance is the expected value of the squared distance from that mean. Why the square? Two reasons. It kills the sign. So a value below the mean and one above both count as genuine distance instead of cancelling. And it punishes far-flung outliers harder than nearby ones. Back to our chart, with the mean marked at 2.25. Each value sits some distance from that line. It's deviation. Value 5 is far to the right. Value 1 is to the left. Draw those deviations as arrows from the mean out to each value. Square each one, weighted by that value's probability, and add. And that sum of weighted squared distances is the variance. In practice, almost nobody computes variance from the deviations directly. There's a shortcut that's far quicker. The variance equals the expectation of x squared minus the square of the expectation of x. Look carefully at the order of operations because it's everything. In the first term, you square each value first, then average. In the second, you average first, then square that single number. Same symbols, opposite order. These two are equal only when there's no spread at all. The gap between them is exactly the variance. Remember that, and you'll never mix them up. One loose end. Variance is measured in squared units. If x is in rupees, the variance comes out in rupees squared, which is almost impossible to picture. What on earth is a squared rupee? So we take the square root and land back in the original units. That's the standard deviation. The same currency as x, a plain, honest measure of how far a typical outcome strays from the mean. It's the number people actually quote. Let's make all of this concrete with job A. X is the day's earning, 900 or 1100, each with probability 1/2. We'll find the expectation, the variance, and the standard deviation in order. Step 1. The expectation. 900 times a half plus 1100 times a half. That's just the midpoint, 1000 rupees. The long run average earning. Step 2. The expectation of x squared. Square each earning first. 900 squared is 810,000. 1100 squared is 1,210,000. Then average those. It comes to 1,010,000. Step 3. The shortcut. Variance is e of x squared minus the square of e of x. 1,010,000 minus 1,000 squared, which is a million. The difference is 10,000 rupees squared. Finally, the standard deviation, the square root of 10,000, which is exactly 100 rupees. And look how neatly that lands. The two earnings, 900 and 1100, sit exactly 100 rupees below and above the mean of 1,000. The standard deviation caught that spread perfectly. A richer example, with three values. X is 1 with probability a quarter, 3 with probability a half, and 5 with probability a quarter. A quick sanity check first. The probabilities add to 1. So this is a valid distribution. The expectation, a quarter, plus 3 halves, plus 5 quarters. The two outer quarters make 6 quarters. That's 3 halves. And with the middle 3 halves, the total is 3. So the mean is 3, which makes sense, sitting dead center. For the expectation of x squared, square the values first, 1, 9, and 25. Then wait and add. A quarter plus 9 halves plus 25 quarters gives 11. Now the shortcut, 11 minus 3 squared, that's 11 minus 9, which is 2. So the variance is 2, and the standard deviation is the square root of 2, about 1.41. Now watch the transformation rules earn there. Keep. Define a new variable y as to x minus 1. We can get its mean and variance instantly, without touching the distribution again. By linearity, the mean of y is 2 times 3, minus 1, that's 5. For the variance, the shift by minus 1 does nothing, and the factor of 2 comes out squared. 2 squared times the variance. 4 times 2 is 8. Sanity check the mean directly. Y takes the values 1, 5, and 9 with the same probabilities, a quarter, a half, a quarter. Its average lands right at 5, exactly as the rule promised. Your turn. Here's a small game. Your net payoff x is minus 1 with probability 2/3. You usually lose a little. Or plus 2 with probability 1/3. Pause the video now and find the expectation, the variance, and the standard deviation yourself. I'll wait. Here's the walkthrough. The expectation, minus 1 times 2/3 plus 2 times 1/3. That's minus 2/3 plus 2/3. Exactly 0. A perfectly fair game. For the expectation of x squared, square the payoffs first, 1 and 4. 1 times 2/3 plus 4 times 1/3 is 2/3 plus 4/3, which is 2. So the variance is 2 minus 0 squared, just 2. And the standard deviation is the square root of 2, about 1.41. Notice the mean is 0, yet the spread is real. The game is fair on average, but far from risk-free. If you got that, you've truly got this. Trap 1, and by far the most common, confusing e of x squared with the square of e of x. One squares then averages. The other averages then squares. They match only when the variance is 0. Trap 2. Squaring the wrong thing. The square lands on x minus mu, the deviation, never on the probability. The probability is just the weight. Trap 3. Misscaling the variance. When you scale by a, the variance scales by a squared, not by a. And adding a constant b changes the variance not one bit. And trap 4. Mixing up variance and standard deviation. Variance lives in squared units. The standard deviation is its square root, back in the original units. Always check which one you actually need. Let's lock it all in. Expectation is the center. Every value times its probability, added up. The balance point of the distribution. Variance is the spread. In practice, use the shortcut. The expectation of x squared minus the square of the expectation. Take the square root and you get the standard deviation, the same spread, back in the original units, the number you can actually feel. And when you scale and shift, the mean scales and shifts with it, while the variance picks up the constant squared. Master these 4 lines, and you can summarize the center and the risk of any discrete distribution at a glance.